Hi, in this video I'm going to show you hypothesis testing, density functions, and how to create new random variables in Stata. So you can see that I've already brought in this data set auto.dta that comes built into every copy of Stata. It contains information on cars which were sold in 1978. So if I wanted to look at the relationship between prices and the gas mileage for these cars, I could do a scatter plot of price against miles per gallon. Here's what the scatter plot looks like. It's got this slightly curvy relationship, so maybe if I model price as a function of miles per gallon, I might want to include a squared term for miles per gallon. So let's first of all create a squared term. So I'm going to create mpg2, which is going to be equal to miles per gallon squared. And now let's do a regression of price on miles per gallon and miles per gallon squared. Okay. Here are the coefficients. And if we wanted to test whether there was any relationship between a car's gas mileage and its price, of course, for there to be no relationship between the gas mileage and the price, it would have to be the case that the coefficient on both miles per gallon and miles per gallon squared would have to be equal to 0. And of course, we can look over here at these p-values. These p-values are like really close to 0, so probably we can guess that we'd be able to reject that they're both equal to 0, but to do it formally, we'd want to run a test of the joint hypothesis. And you can do that using the command test. So I'm just going to say test mpg, mpg2. This is a post-estimation command. This uses the results of this regression. It's going to create a joint hypothesis. The hypothesis has two parts. The null hypothesis is that the coefficient on miles per gallon is equal to 0, so beta mpg is 0, and beta mpg squared is also equal to 0. Beta mpg2 is equal to 0. And you can see Stata generates the f value, and most importantly, it gives you the p value for this. So you can see at any conventional significance level, we would reject that there was no relationship between miles per gallon and price. Of course, we could also do this with other variables thrown in. I could throw in like headroom, trunk, weight, length, foreign, bunch of additional variables, basically capturing that the cars are different sizes. And now when I go back and I test, of course, you'll see that the test is updated for the most recent regression. And you'll see that the F statistic is now much smaller, and the p-value is 0.81. So now at any normal significance level, we would not be able to reject the belief that there is no relationship between miles per gallon and price, conditional on these other variables. Okay, so this is one kind of hypothesis which you can test, one kind of joint hypothesis you can test. Of course, there are other kinds of hypotheses you can test using the command test. I could, for example, test whether the coefficient on foreign was equal to, 5,000. So here when I say this, I'm giving an expression. Now we're testing that beta foreign is equal to 5,000, and we get a p-value for that exact test. We can also do this with these equality signs. I could do, let's say that I wanted to test that, length and trunk have the same. I have no idea why they would have the same coefficient, but let's test whether they do have the same coefficient. So you can see Stata rewrites this as saying that negative beta trunk plus beta length is equal to 0 is the null hypothesis, and the p-value is 0.22. So I guess we just don't have a big enough sample because we're not able to reject that these coefficients are equal to each other, even though I have no reason to believe that they would be. So that's hypothesis testing using the command test, which I think is a really handy command for Stata. Of course, if you wanted to, you could do hypothesis tests by hand by calculating the test statistic for yourself. And then you would take this to, let's say, for example, this you would take to an F table, a table for the F statistic, and then you would look up what your critical values were. You'd look up what the p-value was. Of course, if you didn't have a table handy, like an F table or a normal distribution table, you can also look those values up in Stata for yourself. And the best place to look for the functions which will let you do that is using the help file help density functions. So here we go. So let's say I wanted something about the normal distribution. I'm going to click where it says normal, Gaussian, etc. So let's say here's a function called normal of z. So you give Stata a value of z. You type some number there. Your number should be somewhere between a really large number and a really negative number. And it's going to spit out a number between 0 and 1. And that number is going to be the probability that if you drew a number at random out of the normal distribution, that number would be less than the number that you typed in. So let's do this. So display, I'm going to say display normal for 0. So of course 0 is the median in the normal distribution. So half of the time you get a number which is less than 0. Or if I did this with 1.96, then 97.5% of the time I get a number which is smaller than 1.96. That's the reason why it's the critical value for a two-tailed test for the 5% level. Okay, and then of course you could also do this if I wanted to do inverse normal. That'll just flip around what we're doing. So if I wanted to get the number below which you will get that, a number such that you will get below that number exactly 97.5% of the time when you draw from a normal distribution, that number is 1.96. Okay, so this is just a reverse of what we saw. So those are the density functions, and of course you can look through this help menu to see more detail about what density functions are on Stata. There are lots of them. Another thing which you might be interested in doing is creating new random variables. So you would do this. So let's say, for example, I wanted to create a variable which I'll call x very creatively. And I want to make this drawn from a uniform distribution. Then I can just say generate x equal to r uniform, like random uniform. And then there are these like parentheses there. That's Stata's convention. When it's generating a random variable, is you always put the parentheses there at the end. Browse over here. We'll find this new variable, and you can see here x is drawn from a standard uniform distribution between 0 and 1. So there are the values that we got, and you can see it's different for each observation. Okay. We could also do this with, let's say, a random draw from a normal distribution. So in this case, you go r normal, and then these open and close parentheses. We can even define it so that it's, let's say, a random normal plus 4 times this variable which we just created a minute ago. So now when we browse this, we get these y's, which are maybe a little bit more spread out because they have this component from a normal distribution, which is sometimes going to be negative. And then, so the reason why you might be interested in creating these random variables is, for example, to run a simulation. So if I wanted to run a simulation which tests whether regression works, I could say, well, I created y to be equal to 4 times x plus some normal. So let's run a regression of y on x and make sure that the coefficient is equal to 4. So here's the coefficient, and you can see that 4 is comfortably inside the 95% confidence interval. So let's test that x equals 4, and there you get a p-value of 0.43. So that's nice. So you can see this is helpful for running simulations, or in some few cases you might be interested in creating some random variable for an application of some kind.